Hi, everyone. This is our Applying a Convolutional Neural Network presentation. I'm Kennedy Maloney. My partner is Jonathan Alcala. We are Group 18. So a bit of our table of contents. We'll do a project overview, move into data preparation, model development, evaluation and tuning, results and takeaways, and then our reflection questions. So for the project overview, our goal was to classify Etsy product images as the official Razorback logo classified as 1, or not an official logo, classified as 0. Our data set was over 100 images that we collected manually from Etsy. The framework was using a PyTorch sequential CNN for binary classification, and our focus was model design, training behavior, overfitting control, and tuning. So we went from data to pre-processing to the model to evaluation. So when it came to making the data set, we used the search terms Razorback, Arkansas Razorback, and then I also threw in Arkansas Razorback merch to get some clothing items and like these tags and pins and such that also have the Razorback on them. And we included the official Razorback logo from the U of A branding site that is called Razorback One. So it's what I built the data set off of. And then we used the file name convention R and then a number, and that represented a Razorback one, and then else. I chose candles, so I called them C, and then a number, and then that was what was not a Razorback, so that was our 0. When it came to the splits in the pre-processing, we resized all the images to 500 by 500, like the requirements were for the assignment. And then we applied certain augmentations. We did a center crop, and then we flipped it randomly on horizontally. And then we converted the images to tensors, created the custom PyTorch dataset from that, and then built our data loaders. So for model development, obviously we did a CNN. We ended up doing 4 convolutional layers, max pooling, and ReLU activation, dropout for regularization, and then the most important part that I think improved some of our model accuracy toward the end was the adaptive average pooling layer into the flattening, into the linear, into the sigmoid. So the reason we chose this was because it is small. It's only 4 convolutional layers, and it's efficient. It didn't take too long to run. Running 5 epochs of all the models with a couple of different hyperparameters, like Jonathan will talk about later, um, only took about 10 minutes for my computer. So it's very efficient. It avoids overfitting, again, because we do that adaptive average pooling layer and then flatten it and then do the linear and then do the sigmoid. Um, and this was ideal for the limited data set size that we had. Obviously, in comparison to something like the Celeb A data set, we're definitely looking at a very small sampling size, so we need to not overfit, but still gain some accuracy from the data. So the baseline model performance, these are the train and validation accuracies and loss. Loss is on the left, accuracy is on the right, per epoch. So the training accuracy, it began at 48.33%, but we eventually got it to 51.67. And the validation accuracy did stay the same at 52.38%, but our test accuracy, we got to 70%. So the behavior was that it was underfitting, not mild overfitting. Um, I ran this model with the images being 176 by 176, so a bit of a smaller crop. And the model was able to identify it much better, I think because the model has to take in so many pixels that it's sort of guessing. But as we see, with some pretty moderate accuracy, so no real worry about overfitting here, but some slight worry about underfitting. So on the hyperparameter tuning, we did the learning rates and then dropout values. So we tested the following learning rates: 0.001, 0.0005, and then 0.0001. And then for the dropout values, we did 0.3, 0.5, and 0.7, with our overall goal being to improve the validation performance and stability. So ultimately, the best model ended up having a good validation stability. with a learning rate of 0.001, and the best regularization was a dropout of zero point 0.5. The high dropout did cause underfitting, again, because we have so few layers, and while they all have many inputs, skipping over those nodes doesn't really help the model out in this situation. It kind of hurts it. Um, and a very, very low LR slowed the learning. What was interesting is I decided to play with some of the really, really extreme learning rates. And I did see that the smaller you go, the better it learns and the slower it learns. But I think it paid off in the end for this model in particular. And then, as you can see from the training curve, there's a lot of improvement, and our validation accuracy ended up peaking at 57.14, which we were really proud of. So the final evaluation of it all was the confusion matrix. This is where we see some of that underfitting. Um, True positives, 8. So things that weren't Razorbacks, 8. True negatives, 3. False positives, 2. False negatives, 7. It has strong performance on the non-Razorback images, where I would like for the model to improve in the future is on its classification of Razorbacks. As we can see, um, sometimes it doesn't really catch all of them. And given the purpose of this model, which would be to recognize officially licensed logos, I would say we need to beef up the performance of it being able to identify a Razorback more accurately. So our takeaways was model generalization. It performs well on non-Razorback images, so a high true negative rate, while it does struggle to identify Razorback logos, low true positive rate, many, many, many false negatives. And again, for the point of this model, that's not really what we were going for with this use case. But we did manage to control overfitting with a dropout of zero point 0.5, and the validation accuracy didn't collapse when we did that. And then the training and validation curves improved together in later epochs, which I think is what led to that higher test accuracy. And then opportunities for improvement. This is definitely just a limited data set issue. Additional training images could significantly boost this accuracy. I think we have a good architecture to build off of, but I think it could benefit from more images, more training, more validation, and more test.
Perfect. And now we'll go into a bit of reflection and, looking over some concepts. So the first thing is for our data set, looking at data set creation and splitting. So for our data set, we manually collected just over 100 images from Etsy using keywords like Razorback and Arkansas Razorback. We also included the official Razorback logo from the university's branding site to ensure we had at least one clean ground truth example. And then we labeled our images using a simple file name as mentioned before. Anything with R was treated as Razorback, and everything else was labeled as non-Razorback with the C. And we also made sure to choose clear representative images and avoided heavily edited or stylized versions that would be too hard for a small data set. And then we split everything into training, validation, and test sets so we could evaluate generalization properly and avoid leaking information from one set to another. And then why did we choose our specific CNN architecture? So again, we chose a lightweight CNN architecture because our data set is fairly small and deeper networks would overfit quickly. The four convolutional layers let the model learn increasingly detailed visual features, starting with edges and shapes, and eventually identifying the Razorback specific patterns. We use ReLU with max pooling to improve feature extraction and reduce spatial noise. Dropout helps us prevent memorization, which is especially important with limited data. And then adaptive average pooling gives us a consistent output size regardless of the input resolution. Finally, we use a single dense neuron with the sigmoid activation, so the model outputs a simple probability for Razorback versus not Razorback. This keeps the architecture clean and well suited for binary classification. And then monitoring and mitigating overfitting. So to monitor overfitting, we tracked the training and validation loss and accuracy curves across every epoch. Any early separation between those curves would indicate overfitting, and we actually observed this a few times during tuning. Um, To mitigate this, we use dropout, which helped reduce co-adaptation of neurons. We also applied data augmentation, such as random horizontal flips, to give the model more visual variation without needing more real images. Finally, we ran a grid search across learning rates and dropout values. This allows us to pinpoint which configurations were stable and which led to underfitting or inconsistent validation performance. And then just looking ahead for future improvements, the easiest way to improve the model is to gather more diverse training images, especially more Razorback examples and more negative examples. Another big improvement would be training transfer learning using models like ResNet or MobileNet, which are pre-trained on millions of images. That would dramatically boost feature extraction on small data sets like ours. And then we could also use more advanced augmentations such as rotations, zooms, color jitter, and lighting changes to create wider feature space. And for more advanced optimization, we could explore Bayesian tuning or random search instead of simple grid search. Lastly, if the data set becomes unbalanced, using class weights or sampling strategies would help maintain fair performance across both cases. And this concludes our presentation. Thank you for watching.